Well, welcome everybody. Thank you for joining. So I will try to also actually tell you something about quasi-linear models. And so I will start with a very classical flow. So this very classical flow, and I apologize for those of you who are getting sick about that from Bernard von Karman Street. So this is the flow behind a cylinder, and we know that it has a threshold in Reynolds number, and that for Reynolds less than typically 47, the flow is steady, and above it becomes unsteady. And that bifurcation is super critical. It is a supercritical Hopf bifurcation because it ends up on limit cycle for Reynolds number above 47. So those two pictures are taken from Van Dyck's album of fluid motion. Now, so coming back to that simulation, you see here that there's a spontaneous evolution towards the vortex street. So these type of flows are called oscillators, to oppose to amplifiers, which I will discuss later. And the mechanism behind this, sometimes called global instability, I'll also come back to that later, is related probably to the fact that in the wake of the cylinder, the wake flow, which is almost parallel, quasi-parallel, is actually absolutely unstable. But that's not today's topic. So now, if you look at a little bit more in detail on a transient direct numerical simulation, and here you start two simulations independent for out of phase initial conditions, then you see that the flow evolves from an initial steady state with a non-visible initial perturbation, which is too small to be visible, and reaches at some point this limit cycle, which is here represented by a snapshot. And what's interesting is that you clearly see two phases, an exponentially growing instability phase first, and then a saturation phase. And so this is here materialized in a semi-log plot, where you see the log of the amplitude of the perturbation as a function of time. And there are clearly these two steps visible, an initial exponential growth phase and then a saturation phase. And the idea is to come up with a model which can sort of capture both. So not only the initial linear phase, but also the nonlinear phase. So that's very natural. Now, I will very briefly recap the linear stability idea. It's very simple, but I still need just for later to describe it. So I start from a perturbation expansion, which considers a stationary base flow, okay, and perturbations U prime, P prime. And these base states can be considered either as a two-dimensional flow, or at least a flow which has all the directions of independence of the geometry. So in that present case, it would be capital U of X and Y and capital P of X and Y. So that would be sometimes called the global approach, or since the flow is predominantly dominated by streamwise components of velocity, you could also consider a spatially varying weakly spatially varying flow, which is mostly streamwise oriented, and then you would go for a local approach, which is to consider the wake profile U of Y at different locations. So this is not the way we're going to go today. Today we go for the global approach. So that means that we need first to solve this steady flow, and it is actually a solution of the nonlinear steady Navier-Stokes equations written here. And it also means that if now we look at the perturbation equations, we recognize the advection of the perturbation by the base state and vice versa, and also here a nonlinear term, which in a linearized framework can be neglected. Now, if on the top of that, we take benefit of the fact that the base state is time invariant, we can do an exponential dependence ansatz for the time dependent, exponential to the sigma t, where sigma has a real part, which is the growth rate, and omega here, which is the frequency, and which can be turned into a Stroll number if you divide it conveniently by 2 pi. Okay, so what you see here is that you transformed your linear partial differential equations in time x and y into an eigenvalue problem with still a PDE in x and y, but now a generalized eigenvalue sigma that you need to find. Why generalized? Simply because the sigma doesn't pop up into the divergence-free equation. And so that's why it's called a generalized eigenvalue problem. Now, you need to solve simultaneously these two problems, finding the base state and solving for the eigenvalue problem. So the way you're going to do this is different for both problems. The first one will require an iteration method, like a Newton method. The second one will require another type of iteration method, like a Krylov-Arnoldi method. So in the present, just for as a purpose of an example, you don't have to do it, but you could discretize these problems with finite elements, and for instance, use free fem plus, which we do a lot in the lab. So that goes together with writing a mesh. I mean, defining a mesh here, triangular, defining your finite elements. So we will use P2, P2, P1, P2 for the 2 component of velocity and P1 for pressure, which ends up on roughly a million of degrees of freedom in that case. This is not the purpose of this talk, but I just wanted to illustrate that. So now let's apply that to the cylinder flow. So that has been done very early on by Jackson and Zebib in '87, and then repeatedly since then. So you see here is just a subpart of the spectrum. The spectrum is very, very full of eigenvalues given the size of the matrix that you consider. But still, here are some of the dominant, let's say, least stable eigenmodes. And you see that one, with the cross here, is actually unstable. So now it became a round. And if you look, so if you look at it, it is associated to a leading unstable global mode, which has alternated regions of high and low velocity, which are reminiscent of a von Karman vortex street. Okay. Now you can look at the evolution of the growth rate as a function of Reynolds number, and that's a very nice way to identify the threshold. You see at around 46, 47 that the growth rate goes from negative to positive, which is why it's a supercritical bifurcation, and Hopf just because the imaginary part of the generalized eigenvalue is not zero. Okay, so you're stable in that region and stable there. I know everything of this is simple, but I wanted just to recap briefly. So now if you use the imaginary part omega, you can come up with the dependence of the Stroll number viewed from a linear point of view as a function of Reynolds number. Okay, and so where it becomes interesting is to try to compare that now, this linear, so that's a linear prediction about the oscillation frequency of your von Karman vortex street, and to try to compare that to DNS. And you see actually that the frequency is not well captured at all. And you could have anticipated that by looking here for Reynolds 100 at the snapshot I showed you earlier. You see that the initial period between two peaks, which corresponds to the initial frequency of here 0.74, actually changes a lot during the saturation. And the final oscillation has actually a period which is much shorter. Okay, so there is a significant frequency correction, which is here captured as a function of Reynolds number, but it's not captured in the right manner. And this goes together with the fact that the flow is also not well predicted. You see here the base state and the eigenmode associated to it, which I showed you earlier in black and white. And you see here, thanks to this phase averaging, a mean flow and a snapshot. And you see that they don't look the same. In particular, the recirculation region, which is a very important quantity, is very different in the base and in the mean flow also. And also the snapshot, let's say the vortices are not located at the same position at all. They are much closer along the limit cycle to the cylinder than they are in the eigenmode based on the base flow. Okay, and so now the frequency prediction here from a paper of Benoit Pierre in 2002, where you compare the linear prediction from a linear base state and the experiments from Williamson and some DNS, direct numerical simulations, you see that the agreement is accurate only close to threshold at 47, but deteriorates almost immediately. Okay, and again, the reason for that is that the mean flow is not well predicted. So you see it here by reporting the recirculation length as a function of Reynolds number. And you see that after threshold, if you just consider the base state, this recirculation bubble elongates. However, if you look at the mean flow, it shortens. So that means that the mean flow here and the base flow here are extremely different, even for Reynolds number as small as 60, 80, or 100. So that has been early understood also in the transient experiments of Thierry and Westfred, who clearly showed that as we start from this numerical simulation, and if we start from a base state as initial condition and we leave it through an exponential instability that I described earlier, then progressively the recirculation length shrinks until it reaches its saturated value on the limit cycle. So that's a summary of what I told you. We start from a base state with a certain eigenmode. That eigenmode, even if it's small, generates small to the square but still existing Reynolds stresses. And those Reynolds stresses force the Navier-Stokes, the steady Navier-Stokes equations to change the base flow into a mean flow progressively. And when you reach this sort of balance on the limit cycle, you have the mean flow, which results from the steady Navier-Stokes equations forced by the Reynolds stresses obtained from the instantaneous Reynolds stress associated to the snapshot. Okay, and in that process, you change the frequency a lot from here, almost 60%. Okay, and so another way to think about that is just to take that mean flow as a given. Imagine you had a way to measure it, and then do a stability analysis on that mean flow. And that was done again by Peer using a slightly different approach. But what he found is that the prediction from the linear stability analysis on the mean flow here in blue is actually much more relevant, and it's a very good approximation of the limit cycle frequency. Okay, in contrast to the linear stability analysis of the base state. And not only is the frequency well predicted, but as shown by Dwight Barclay in 2006, the growth rate, which you can compute on the mean flow, here taken as given, is 0. Okay, so we have all the ingredients to understand what's going on. We have actually a flow that generates an instability, and this instability forces the base flow to become a mean flow and to change through the retraction of the Reynolds stresses. This mean flow progressively becomes neutral or marginally stable, if you want. And as it does so, it reaches a limit cycle. Okay, and so I here borrow an image that I took from Brian Farrell. So this is in a way a little bit similar to what centrifugal regulator. So in old engines, whenever the rate of the motor was becoming too large, then the centrifugal force would actually push away these heavy balls, and as it would do so, it would progressively close the throttle. So this is of course a madman artificial regulating controlling mechanism, feedback mechanism. And so the idea is that the flow by itself has the ingredients to do the same things. So it has a base state which can be modified through the Reynolds stresses, which are actually here these sort of balls. The perturbations are the balls, and they change the throttle opening to maintain a permanent regime. So it's not a perfect analogy by far, but I think it's a useful analogy to think of. So of course, this is not new, what I'm showing you. And these ideas were in the literature for a very long time. It started maybe with the brother of Emily Nutter in a very old paper. Malkos was mentioned already by Steve Tobias, Stuart, obviously, many others, and some of the literature from the geophysics community, some of the references from the geophysics community I know less, but I can, these are just examples. And there is a clear link with some other approaches of statistical steady states by Farrell and Ioannou, and also the very clear explanation about the CE2 approach by Stephen Tobias a minute ago. Okay, now these also, if somebody can close his microphone, I have a feedback. Maybe I should.
Can everybody close mute their microphones, please? Only the speaker should have the microphone on.
Thank you so much. And so this has also some link with the so-called RZIF property, real zero imaginary frequency property, by Turton and collaborators, including Laurette Tuckerman. And we will have more in the talks later on that. And this has also been used to justify stability analysis on mean turbulent flow. So there has been in the 60s, 70s, 80s, a couple of studies where people would go in the lab, measure average properties of turbulent flows, and do stability analysis on the top of them. But the purpose of my talk today is to show you that you don't need to take the base state as a given. You can try to compute it as part of the process of computing the stability properties of a flow, you simultaneously try to compute the mean flow, of course, making some assumptions, and its stability property. And this is actually a quasi-linear model, exactly in the spirit of what Stephen Tobias has explained to us earlier, which we reinvented and unfortunately coined differently, self-consistent, but it is nothing more than a quasi-linear. Anyways, so I start as usual from the Reynolds decomposition. I recognize here this equation here, which is the equation for the mean state, and I recognize the fluctuation equation. And so what I'm going to do is that I'm going to keep this Reynolds stress interaction in the mean state. So that's a time average of the Reynolds stresses. In that case, it's a time average, but I could use the phase average, like we said, or a spatial average. And then when I'm going to use the linearized dynamics, but around that mean state, not around the base state. That's the main difference. And the harmonic contributions, I will neglect. Okay, and again, this is a similar bet as before in the previous talk. We have no a priori guarantee that this could work, and so we will do it and see what we get. And so in that present situation of the flow behind a cylinder at Reynolds 100, I'm here extracting from a DNS the first harmonic contribution at the frequency of the prevailing limit cycle, but also the second harmonic. And if I compute here in blue the energy associated to it using the same color bar, I see that the energy which is contained into the second harmonic is only 5% of that which is contained in the first harmonic. So that's a sign, it's not a proof, but it's a sign that this is a flow which is likely to be favorable to neglect that second harmonic just because its energy contained is little. It doesn't mean that it doesn't play a role. It could perfectly play a very important role, but at least it is not energetically very significant for that Reynolds number. So if I neglect these harmonics, the equation for the fluctuation becomes standalone. It's not forced. Okay, so I can solve it using an eigenvalue. Okay, and I call that eigenvalue sigma or lambda, whatever you want. Here lambda. And what happens is that since it's a linear problem, I will find an eigenmode and I will find an associated eigenvalue, lambda 1. But that eigenmode doesn't have an amplitude. So the amplitude is a free parameter. So I take this amplitude as a free parameter. I solve that problem, which is linear, so it doesn't care about the amplitude. And I feed back the amplitude only in the Reynolds stresses divergence into the steady Navier-Stokes equations. Okay, so that's a closed system. It's not necessarily easy to solve, but it's a closed system which you can solve by different methods. Let's say either quasi-time stepping or maybe some Newton method, whatever you like. Okay, and so again, I want to insist that this is very, very similar to similar approaches in different contexts. And we should discuss if this is the right thing to do here, time averaging or ensemble averaging or whatever we want to call it, or spatial averaging, etc. Good. So now we have solved that problem for you, and you see that the real part of that eigenvalue, sigma 1, is decreasing as I'm changing the amplitude, which is a free parameter. So I need to solve that problem for every single value of A. Actually, I do that by the continuation method. I use A as a continuation variable. And I find that after a certain value of A, I can make the system neutral. So there is a specific value, let's call it A star, for which sigma 1 star is 0. Okay, so there is one way to get a perfect balance or self-consistency, if you wish, between the perturbations which live on a mean which itself is driven by those very exact perturbations with the right amplitude. Okay, so everything has to be consistent. So this is just a way to formalize the papers I mentioned earlier, and it's also a way to compute everything together. Now, does it work? It does reasonably. Here you see the evolution of the Reynolds stresses, which are responsible for that saturation mechanism. So initially they looked exactly like those that you could compute from the perturbations on the base state, and progressively they migrate upstream. Okay, now a comparison between this self-consistent approach, its mean flow at Reynolds 100, the associated Reynolds stresses, and the associated eigenmode, compared to the mean flow Reynolds stresses, and fluctuation. The fluctuation are slightly different. This is exactly because in the fluctuation, there is the 2 omega component, which is not important in terms of energetic content, but it's very important in terms of symmetry breaking. And as noticed by Laurette Tuckerman a couple of years back, in particular, the classical symmetry breaking double symmetry breaking in the von Karman vortex street, which is this alternation of vortices, results from that second harmonic vorticity contribution. Okay, so agreement regarding the base state, we measure here the recirculation length, and we see that the DNS here in red is very well predicted by the self-consistent, whereas the base state, if I continue Reynolds number, doesn't go the right way. And finally, a comparison of the frequency. The frequency is very well predicted. 2, we see here comparison between experiments, some stability analysis by Dwight Barclay on the mean taken from average DNS, and our self-consistent approximation computing the mean through the consistent mode. As far as the amplitude is concerned, it is reasonably well predicted too. Good. I think the time is flying, so I will skip these details here. I just wanted to show you that since the growth rate is rather small, at least if your Reynolds number is not too far from threshold, you can here you see you start with 0.15. You might try to separate timescales and separate the growing rate from the intrinsic frequency of the oscillation, which opens the floor for a weekly non-parallel in time, so quasi-steady is a more precise approximation of the flow, which is given here. And so you use your quasi linear self-consistent analysis I showed you before, just to predict the time evolution. And it works not perfectly. We missed the overshoot here in red, but it works reasonably well. So I skipped those details because I'm lacking time. What I would like to do instead is point to the fact first that this marginal stability property, R-ZIF property, so the fact that the limit cycle is very well predicted by a mean and its harmonic being neutral, is not always true, by far not. Okay, it doesn't always work, and there are counterexamples in double convection, for instance, by Laurette Tuckerman and collaborators, and there are many more examples where this quasi-linear approach, which doesn't capture the feedback of smaller scales onto large scales, fails. Still, I want to show you another situation where it works pretty well, and I think it's interesting because it's a situation where the let's say modal analysis, so the stability analysis, which looks at eigenmodes, fails. So this flow, which you see here in the back and the bottom of this slide here, is a flow that has been studied a lot since 20 years. It's the flow behind a backward-facing step. Okay, so it is convenient to numerically simulate, and it is very interesting because this flow, if you compute the spectrum, I'll show you an example in a minute, is actually stable. So it doesn't have any unstable eigenvalue, but it has a very strong shear instability, Kelvin-Hamilton stability, which is known to give rise to a very intense amplification of incoming perturbations. So in absence of noise, you don't see anything, but for the little noise you can think of, you start seeing something. These type of flows are often called amplifiers. They have extrinsic dynamics. They need perturbations to be provided either as initial conditions or as sustained harmonic forcing or as external noise. And so I promised you a spectrum here, actually for Reynolds 200. I forgot to put the Reynolds number, I apologize. You see that all the eigenvalues that we could compute are actually stable. So they have here a growth rate, here symbolized by omega y, which is negative. Still, again, because of that very intense shear layer between high velocity here in red and small velocity here, or negative velocity in blue, because of that very intense shear, they amplify a lot. How can we understand that? We need to come back to the same strategy. We need to decompose into a steady mean flow and a fluctuation. We can look at small forcing amplitudes, introducing a small forcing amplitude epsilon, and we can solve it order by order. At leading order, the epsilon being small, there's no feedback of the perturbation, and so we get the base flow equation. And at first order, we get an equation which this time is not a standalone eigenvalue equation with omega here an eigenvalue, but it is instead a forced equation which has an operator here, which is a stable operator, but it has here a forcing. Okay, it's linear still, it's epsilon epsilon, so it's linear, but that's a transfer function or a resolvent, it's called very often. And omega here is prescribed, not it's prescribed by the harmonic forcing at which I'm forcing the system. Okay, so here on purpose I choose harmonic forcing. And so these operator I told you is known under the name of resolvent, and it is a very convenient operator to analyze the stability properties of stable flows, which still have a huge amplification potential. And you see here the maximum gain over which, so here you optimize over the forcing structure F, which you see here, it's a bit complicated, but that's the way you should force the system to get maximum gain out of it. And so if you force with that F, you get a gain of several thousands, depending on the Reynolds number, and you can even show that this gain grows exponentially with the Reynolds number. Okay, and so here's an example of the optimal forcing at a certain strong number and the response. So the fact that they are not the same points to the fact that the flow we consider and its linearized operator is not normal, and it is not normal because of the intensity of the convection. So now the talk today is about nonlinearity, not non-normality, but nonlinearity. So here we have non-normality and non-linearity. And the proof that we have non-linearity, I will show it again because I was too slow in my transition, is that if you force at a 10 to the minus 4 forcing amplitude or 10 to the minus 2, you don't get the same result at all. So in the first case, you saturate your waves pretty far. And the reason is that since you force with small amplitude, you need a lot of distance to have your Kelvin-Helmholtz saturation. In contrast, if you force with epsilon 10 to the minus 2, since the Kelvin-Helmholtz instability is very strong, you saturate much earlier. And that goes with a gain, which is not the same at all. So you see that for a value of 5 to 10 to the minus 3 of forcing, you reach a gain which goes from 8,000 to less than 1,000. So you divide your gain by more than 10. So the effect of the saturation, which results from the saturation and growth of the response to the harmonic forcing, is extremely impressive. And so in terms of response, instead of following a linear response here in black, you saturate the response very strongly. Okay, can we capture that? So one attempt, which is very natural, would be to try to use an asymptotic analysis. Okay, a naive expansion, so you know that you have a small forcing F, so you expand at different orders. So I will skip the details, they're not interesting, it's a straightforward algebra. But there is a major problem that appears, is that for epsilon small, your series is convergent, but very soon it's not convergent anymore. So these are the results here. You see in red the DNS, direct numerical simulation with the gain. And you see here the first order, which is linear. Okay, so it assumes that nothing depends on epsilon, obviously, because it's a gain, so it's proportional. So the response is proportional to the forcing. But the reality, of course, shows saturation, and we can do a third order, including different contributions. And in any case, what we see is that the deviation from the DNS happens as early on as 10 to the minus 5. Okay, and so there is no paradox here. The asymptotic expansion doesn't have a convergence radius which is large enough to function. So you see here on a different scale that it only works very, very close to threshold, and it predicts a completely unphysical breakdown of the gain at 5 10 to the minus 5. Good. So what can we do instead? We can go for our self-consistent model. So in this self-consistent model, as previously, we will keep the retroaction on the mean flow, okay? So the steady component of the Reynolds stresses, but we will discard the harmonic contributions. And so we are left again with a system to solve, except that now the amplitude is not free because there's no eigenvalue problem, and we know the forcing of the amplitude F. So for every single amplitude of F and shape of F, we can find a balance of those two coupled equations. Okay, if we do this, we get a reasonable agreement. I say reasonable because if we look from far on the gain here, it seems perfect. But if we look at the response, the accuracy is a bit less. So we see that, for instance, for epsilon 10 to the minus 2, we have typically a 10% error by solving these quasi-linear coupled system instead of looking at the DNS. Okay, so that's promising, and it doesn't work only for one frequency. Here's an example of the most unstable frequency, 0.0.75, but it works actually at every single frequency. And we see here the saturation effect caused by a forcing at 5 × 10⁻⁴ at all frequencies. And we see uniform saturation at all frequencies considered here, which is reasonably well captured by the semilinear model. Good, the mechanism is still the same. So as the response migrates upstream, it creates Reynolds stresses, which also migrate upstream. We see them here. And those Reynolds stresses, which are which compare extremely well with the DNS, are responsible for the shrinking of the recirculation region, for the shortening of the intense shear layer, for its widening, and for all these reasons, the instability becomes less and less. Quantitatively, we can compare the length of the bottom bubble and the separation point and reattachment point of the top bubble, and they all agree very well between DNS and self-consistent model. Good. So that was work actually by Vlado Mantic-Lugo, a PhD student of mine a couple of years back. And now the question is, I promised you earlier in my transition that this idea that the marginal stability property can be used possibly to try to analyze turbulent flows. And so in the next few slides, I would like to give you a recent update on the work done by Yunuk Yim, a postdoc in my lab, on the way to try to implement also a turbulent background. And so this is done in what I would call a rather quick and dirty way. I apologize for that, Anok, if you listen to me. But quick and dirty because we are not going to do a statistically consistent treatment of the turbulence. We're going to go for a rough eddy viscosity model. Okay, so the idea is that we're going to separate in a triple decomposition as proposed by Reynolds and Hussein in 1972. In this triple decomposition, we have a time average flow U, we have a coherent fluctuation U hat, and we have an incoherent fluctuation U prime. Okay, and so the idea is to try to compute the mean flow as the result, as being forced not only by the coherent fluctuations as we did just before at Reynolds number, laminar Reynolds number around 500, but to also include this term here, which is actually an eddy viscosity contribution. Okay, and so in the end, we need to couple three things. We need to couple a linear resolvent as before, which is now calculated on the mean flow, U. A mean flow, again, which is forced by the Reynolds stresses of the coherent fluctuations, but also of the inconsistent, incoherent turbulent fluctuations. And we need a turbulent model here, which is an eddy viscosity model, which finds the eddy viscosity in UT as a function of the base state only. Okay, so the idea is that the small scales, incoherent small scales, and the coherent fluctuations never talk directly to each other. They only talk to each other through the mean flow. So that's an assumption which is sometimes valid, sometimes not. And it can be heavily criticized. But the purpose of that work here was to try out that method, to see if we could converge that, because now we need to converge 3 equations instead of 2. So get a consistent solution of those 3 equations altogether. And second, we wanted to check if it was reasonably well predicting results. So for that, we took a NASA test case, which is very well documented from the experimental and different numerical methods, including Urans with sophisticated turbulence models. And this is, again, a backward-facing flow, but this time the aspect ratio is very different. So let's say the step is very shallow. And the Reynolds number is much larger. And so when you look here, these are comparison between a numerical model, including a sophisticated turbulence model and the LDV measurements. And we first compared our Urans, which was based on a spalaral mass model, And we saw reasonable agreement, of course, not in this very delicate region here, where agreement between different numerical simulation, turbulent numerical simulations and measurements was actually never really achieved. Now, if we look at the energy gain, we see that if we change the forcing amplitude and run our U-runs, we see that the gain becomes less and less. This time it's much less spectacular, precisely because of the eddy viscosity. So despite the higher Reynolds number, the energy gain is far less than it was in the laminar regime. But we see that there is a saturation, which is captured by our unsteady run simulations, which were validated before. So then what we did is to run, to solve, not run, but to solve this model here and to compare. So this is what we have done here. So these blue triangles here are the results of the quasi-linear model, which has simplified, very simple turbulent eddy viscosity approach coupled to a linear resolvent and to a nonlinear solution of the base state, of the mean state, sorry. And so we see that the agreement is fairly reasonable. We checked it at also at other frequencies where we also had a reasonable agreement.
Are you finishing, Francois? Because we are already close to the time limit.
Exactly. You see, I'm reaching my conclusions. They will be double-sided if you give me 2 minutes. First, I will close on what I showed you. So it's possible to use the self-consistent model, which is actually a similar approach. It works not only for unstable flows on which you have to iterate on the amplitude of the perturbations to reach the marginal stability property, but it also works for harmonic fluctuations in non-normal convective amplifier flows, but it doesn't always work. And I didn't say much on that, but it's not necessarily very easy to solve either. Just want to show you extensions, which I will not detail, but you can generalize that similar approach to unsteady flows, which are nominally unsteady. So if your base state, for instance, diffuses, so that's the case here of a vortex which has a diffusion, intrinsic diffusion of the base state. You can also use it to do some sensitivity predictions. We have a work with Philippe Méliga and Edouard Bougeot on that, where we show that we can do a sensitivity map of the amplitude of the limit cycle using that model. And also we can try to extend to white noise by trying to represent the white noise as a superimposition of different frequencies, which are the most relevant. So these are just 2, 3 very, very fast just extensions that we came up with, and there are many more, I hope, to come. I thank you for your attention. I want to acknowledge the people who did this work. Landau Matic-Lugo, Cristobal Aratia, now in Sweden, Yuna Kim, who just finished a postdoc in my lab, Edouard Bougeot, who is now back in Switzerland, and Philippe Méliga in Nice. With this, I thank you very much, and I'm happy to take questions.